thank you very much for being here, and thank you for the organizers for inviting me. This is actually the first talk, Blackboard talk I'm giving post-corona, so let's hope I still remember how to do this. Anyway, okay, so first of all, I want to say a few words about algebraic Prym varieties, just as a reminder of what these are, and as motivation for what I'm studying. So these were kind of around for a long time, but the interest in them was really started with, there was a seminal paper of Mumford. So if you have an étale double cover of smooth algebraic curves, so this is an étale 2-to-1 cover. So C tilde and C are smooth algebraic curves. Then if the genus of C is something like G, then genus of C tilde is 2G minus 1. Then you can consider the norm map from the Jacobian of C tilde to the Jacobian of C. And then you can show that the kernel of the norm map has two connected components. And so the connected component of the identity is what's called the Prym variety of this double cover. So there's, this is the connected component that contains 0. And there's also another one, which I'll denote Prym, I don't know, prime. C tilde over C. Okay. And so Prym C tilde over C, this is a abelian variety of dimension, well, the difference of the dimensions. So this map is surjective. So this is an abelian variety of dimension G minus 1. And what's especially important is that this is in fact a principally polarized abelian variety. And in fact, well, maybe I'll write it or I'll just say it in words. It carries a principal polarization, which is exactly half of the principal polarization induced from its embedding into the Jacobian. So there exists a principal polarization psi on the Prym variety such that the pullback of the polarization theta from the Jacobian is 2 times psi. Okay, so why are Prym varieties interesting? Why do people study them? Well, the reason is that there are a lot of them. They are a way of constructing a large dimensional family. See, I don't know how to do this. Okay, maybe something like this. They are a way of constructing a fairly large dimensional family of PPAVs. So if you think about RG, this is going to be the moduli space of étale 2-to-1 covers of a curve of genus G. Then the Prym variety construction gives you a map to a G minus 1, which is the moduli space of PPAVs of dimension G, right? So this is called the Prym-Torelli map. And then if you just count dimensions, so what is the dimension of RG? Well, so it's just the dimension of the moduli space of curves of genus G. It's just, you pick a curve and then you pick a double cover of it. So this is the dimension of MG. And so this is 3G minus 3. Whereas the dimension of AG minus 1 is G times G minus 1 over 2. And so what you can check is that this thing is greater than or equal to this thing if G is less than or equal to, let me make sure I get this right, 6. Okay. So a generic PPAV of dimension 5 or less is in fact the Prym variety of some double cover. Whereas for Jacobian, that's only true for dimensions 3 or less. So you can study moduli space using this Prym construction. That's going to be it for the algebraic geometry part of this talk. It's just a motivation. Everything else I'm going to be doing now is essentially pure combinatorics. Okay, so now I want to start talking about graphs. I'm moving to this board. Okay, so my graphs are allowed to have loops and multi-edges. So loops, multi-edges allowed. So here would be an example of a graph that has both. So this is a graph G. So V of G is going to be the set of vertices. E of G is the set of edges. And the genus of a graph is the first Betti number. So this is the number of edges minus the number of vertices plus 1. Okay, so let me remind you how chip firing works on a graph. So the divisor group of a graph is just the free abelian group on its vertices, right? And so then, so this is just a set of expressions of the form NV times V. These are integers. And so the degree of the divisor is just the sum of the coefficients. Okay. And so if you pick a vertex V in your graph, you can define the divisor D of V in the following way. So for each edge E, which is attached to V, so E is an edge at V, what you do is you take the other vertex, 1 times the other vertex of E. And then you subtract however many edges there were at V. So you subtract valence of V times many copies of V. Okay. So for example, if this is my vertex V, then the divisor D of V. So I'm gonna, for each of these edges, I'm gonna put a 1 at the other vertex. So there's gonna be a 2 here, a 1 here, and therefore a -3 here. Okay, so this divisor is D of V. So this is what's called the divisor obtained by firing the vertex V. Sorry, is there a question?
What about loops?
So loops don't actually do anything because a kind of a chip goes back to. Yeah. So if I fire this vertex, I'm just going to get a -1, 1, and this loop that doesn't contribute. Okay, and so then if I take the, so this is by definition a divisor of degree 0. Div 0 of G. Right? And the set of divisors of degree 0. And then I define the set of principal divisors, then G, as just the subgroup of the divisors of degree 0 spanned by these D of V's. So this is just the span of D of V in div 0 of G. Okay. And so then I can define the Jacobian of a graph as the quotient of the degree 0 divisors by the principal divisors. Okay. And so now a theorem which goes back to, in one form or another, to Kirchhoff. Of course, Kirchhoff didn't know anything about chip firing, but he did know about graphs, and he did know about graph Laplacians. So Kirchhoff's theorem is that the number of elements in the Jacobian, so first of all, I should say this is actually a finite group. And so the number of elements in this finite group is the number of spanning trees of G. Okay. And well, so the way Kirchhoff would have phrased it is it's the number, it is the absolute value of the determinant of the reduced Laplacian matrix of your graph. So for example, this graph right here, as you can easily see, has 5 spanning trees. The order of the Jacobian is G. And of course, loops don't contribute to the spanning tree count, just as they don't contribute to the Jacobian. Okay. So over here. So now what I want to do is I want to define the Prym, well, not variety, this will be the Prym group of a double cover of graphs. How does this work? Okay, so I'm now going to consider f G tilde to G to be a double cover of graphs. And so this is the simplest notion you could have of a double cover. Just think of your graph as a topological space and think of a degree 2 covering space. So just think of a degree 2 topological covering space. So what I'm going to do is I'm going to draw a large example on the board over there and then come back to it once or twice while I keep talking. So I hope that's okay. I'm actually going to start with the graph that I just erased. I'll look at the double cover of it. So from here, this is my graph. So here's what I'm going to do. I'm going to take kind of the interior part without the loop and without this kind of edge on the end. And I'm going to just take 2 copies of it like that. But then I'm going to reconnect them a little differently. This loop, I'm going to lift it like this. So there are going to be 2 edges like that connecting the 2 sheets of my cover. And similarly, this edge, I'm going to start drawing from here, but instead of ending up here, I'm going to end up all the way here. And similarly, this edge is going to go like this. Okay. So this is my double cover. So this is G tilde going to G. Okay. So, so I can define a push forward map on divisors in a pretty obvious way. I just take f lower star of a vertex to be the image of that vertex. So it's clear that this respects chip firing because this map is essentially a local isomorphism on my graphs. So you can check that this induces a map on the Jacobians of the corresponding, so just a homomorphism, a surjective homomorphism of finite groups. Okay, and so what we want to do is we want to say that the Prym group of this double cover is the kernel of this map. Of course, I want to say it's not just the kernel, it's the connected component of the identity of the kernel, but that doesn't make sense for finite groups, right? So what I first do is I prove that there exists a parity map from the kernel of my norm homomorphism into Z mod 2Z, a surjective parity map. This is a fairly simple exercise to show that this exists. And then I'm just going to, this is a lemma slash definition, I'm going to define the Prym group of my double cover to be the kernel of this parity map epsilon. Okay, so that's my definition. And so the question, the first question that I'd like to have answered is, oh, right. How do I find the order of this kernel? Well, so Kirchhoff's theorem tells me that the order of the Jacobian of a graph is the sum of spanning trees. So what I really need to do is find the analog of the notion of a spanning tree, where instead of having a single graph, you have a double cover of graphs, right? And I presumably want to take a sum of such objects, possibly with multiplicities. And well, the rest of my talk is going to be essentially what these objects are and what kind of geometric meaning they're going to have. Okay, so what I want to do, question is I want to find number of elements in this Prym group. Okay. Well, so let's go back and talk just a little bit about spanning trees. So let's say that G is a graph of genus. Okay. So instead of thinking about spanning trees, I want to think about the complementary edge set of a spanning tree. If you've ever done any graph combinatorics, that's kind of a fairly important thing to look at. So what does it mean for a subset of edges of G to be a complement of a spanning tree? Well, so if you think about it for a second, what this means is that removing these edges does not disconnect the graph. And furthermore, the set F is maximal among sets with this property. So F is maximal with the property that removing the set of edges E keeps your graph connected. Right? As soon as you have a tree, every edge is a bridge, and you cannot remove any more edges. And then the number of edges, the number of edges in a set with this property is always equal to the genus of the curve of your graph. Okay, so what I want is some kind of notion of this that makes sense for double covers and not for individual graphs. And so here's what I'm going to do. Actually, so now F is going to be a double cover. And I want to consider subsets E, F of the edge set of the target graph G, with the following property. Removing these edges may disconnect my graph G. But I want it to have the property that every connected component that I have still has connected pre-image in G tilde. Okay, so this is the key property I want to write down. Every connected component in G, remove F, has connected preimage in G tuple. Okay. So I want to remove edges from my target graph so that my cover stays relatively connected, so to speak, that it doesn't have more connected components on the top or on the bottom. And I want to consider F that are maximal with respect to this property. Okay. And so now let's think about what such sets of edges are going to look like. Okay. In particular, let's let's take F to be a subset of the edges of D, and let's assume that the number of edges in F is G minus 1. Okay, so then the graph G minus F might decompose into some number of connected components, let's say K. And then it's kind of an easy calculation to do that the sum of the genera of these GIs is equal to K. The quantity B1 minus 1 is additive in connected components. Okay, but now observe the following fact. If you have K integers which add to K and the integers are non-negative, then either all of them are 1 or one of them is 0, right? Okay. So this calculation leads to the following conclusion. Maybe a little bit more water next time. Okay. Got away now. Okay. So what are the possibilities? Well, one possibility is that one of the GIs is, one of the genera is equal to 0. So G of GI is 0 for some I. But then a genus 0 graph is a tree. A tree has trivial fundamental group, and hence a tree does not have any connected double covers, right? So this tells me that pi 1 of GI is 0. And this tells me that the restriction of the double cover to GI is the trivial double cover because that's the only one there is. So in particular, this tells me that the preimage of GI is not connected. And so this is the possibility that I want to exclude, right? So I'm left with having some number of connected components. Each of them has genus 1. So it's just a cycle with possibly some trees attached to it. So the genus of GI is 1 for all I. And then, well, the fundamental group of a graph of genus 1 is Z. And so there are precisely 2 double covers that you can have. One of them is connected and non-trivial. The other is disconnected and trivial, right? So POM of pi 1 of GI into Z mod 2Z consists of 2 elements. Well, in fact, it is just group Z mod 2Z, right? And so F minus 1 of GI is connected if and only if it is the non-trivial double cover. Okay. So removing G minus 1 edges, as you can see, is kind of like the most that you can possibly remove. Because if you try to remove one more edge, you're going to create a tree as a connected component, and it's going to have disconnected preimage. Okay, and so now for the hardest question that I faced when preparing this talk is, what do you call a set of elements that has this property? Okay, so the definition that we originally gave in our paper with Yoav is that such a set is called an odd genus 1 decomposition. So why? Because it's a way of removing edges so that you're left with a number of genus 1 curves, each of which such that the cover over each of one corresponds to the odd element of the corresponding homology group. And we thought that this was really lame, but then we realized that the corresponding acronym is OGOD. So we thought that was actually pretty cool. And so we stuck with that. And then we did an extensive search, including Facebook polling and whatnot, to try to find the better word. And we actually didn't come up with anything. So I'm just going to stick with OGOD. Okay. So F is an odd genus 1 decomposition if it has this property. So if removing F gives you some number of connected components, all of which have genus 1 and all of which have connected preimage. The only difference between OGODs and spanning trees is that they have an extra invariant, which is the number of connected components that they have. And this number K is going to be called the rank of the OGOD. Okay. So as an example, maybe let's just look at this picture that I have here. So let's give it some names. I'm just going to do it this. E1, E2, E3, E4, E5, E6. So what's not an OGOD? Well, for example, if you remove the edges E5 and E6, you're left with a tree, kind of worse, you're left with an isolated vertex, and the preimage of that isolated vertex is a pair of isolated vertices. So E5 and E6 is not an OGOD. But another thing that might happen is, let's say you remove the edge E5 from your graphs, you're cutting these two edges here, and you remove the edge E1. So then that is a genus 1 decomposition, right? But it's not odd because this cycle here has its preimages to two connected pieces. Okay? So E1 and E5 is not an OGOD. But what is an OGOD? Well, for example, you can remove E5 and E4. So this is an OGOD. Now let's just figure out its rank. So if you remove E5, you're getting rid of these two edges. And if you remove E4, you're getting rid of these two edges. And so that's going to be an OGOD of rank 2, right? Because you have two connected components down here, each of which has a preimage which is a cycle. So E4, E5, this is an OGOD of rank 2. Okay. And so now with this definition, I'm ready to state the formula for the volume of the, sorry, not quite the volume, the number of elements in the Prym variety, in the Prym group. Okay. So, theorem. So if f from G tilde to G is a, well, I'm always considering non-trivial, could have said this, or connected, double cover. Then the number of elements in the Prym group is the following sum. So you sum over all possible ranks, and the ranks can be from 1 to G. Of C to the K, where C to the K is the number of ogods of rank K. But now each of them is weighted with a coefficient which is 4 to the K minus 1. So ogods with multiple connected components contribute much more heavily to the sum. So this theorem was proved by Len, Yoav, and myself. But I've left the room here. Anyway, once we proved it, we posted and we got some comments. It turns out that in one form or another, this result was known for a while. So there's a paper of Zaslavsky from, oh gosh, 82.
Did you say, oh God?
No. Oh God, yeah. So let me kind of explain the history of this problem. So Zaslavsky, of course, he worked before people started thinking about chip firing, as far as I know. What he worked on is instead of what are called signed graphs. So he just said, let's take a graph and put a plus minus sign on each of them, on each edge. And so clearly, if you have a signed graph, you can define a corresponding double cover by just taking 2 copies of that graph and connecting the edges kind of crisscross if the sign is negative and within each sheet if the sign is positive. And so then he defined something called the signed Laplacian of a signed graph and computed its determinant and got this formula without any kind of, without relating it to any other thing. It's just, here's something we can compute. And then Reiner and Tseng later on actually interpreted Zaslavsky's result as actually computing the kernel of the push forward. And then we independently discovered this formula, and Reiner politely informed us that this is actually known. Okay, so now, well, I should probably state the theorem that we did prove that wasn't known before, right? So to do that, I'm going to now talk about metrographs. Are there any questions? Okay, so
Dimitri,
yeah.
Is there like any structure to this coefficient CK? Like, I mean, this is a sequence of integers, right? Does this sequence of integers have any pattern if you go from 1 to G?
Not really. I mean, yeah, I can't say. I mean, it's just, well, actually, I should have done an example. Let me just maybe. So for this double cover here, I mean, more connected double covers will have higher number of ogods, but we couldn't tell any. Yeah, we didn't really think about that question. Yes. Okay. So if you're really bored, you can start counting how many ogods there are in this picture. So there are 6 edges. 6 choose 2 is 15. So there aren't that many to check. So what you can verify is that in this example here, there are in fact 8 ogods of rank 1 and 4 ogods of rank 2. And so the order of the Prym group is going to be 8 plus 4 times 4, which is 20. And so remember that I mentioned that this graph has 5 spanning trees. They're not really hard to count. And so if you're really, really bored, what you can do is you can start counting the spanning trees of this graph. And so this is half of this over this. So you'll get 5 times 2 times 24, so 240 spanning trees. That's what you're talking. Yeah. Okay. So yeah, so let me talk about metrographs now.
Is there a reason why the 4 appears there as number
Yes,
2?
I will. That there is a deep reason for that 4, which
I mean,
I
there
will.
must be a reason, but it's like
It is a pretty profound reason, I would say. Okay, so I am quite a bit. So now let's talk about metrographs. So a metrograph consists of the following data. It's just an ordinary graph G and an assignment of something called length to each edge. So, so this is what's called a metrograph. And so G is just a graph, finite with loops, multi-edges allowed. And there's this L, which goes from the edges of G to, and if you're really fancy, you can look at kind of various monoids, but really I'm just going to look at positive real numbers. So this is what's an assignment of a length to each edge. But it's just, as you'll see, it's ever so slightly misleading to think of this as length. So let me put a little asterisk here, just to kind of put a little bit of doubt in your minds as to why this should be a length. So then, what is the divisor group of? Oh, okay. So out of all this, you can construct a metric space in an evident way, which is just take an interval of length L of E for each edge and reconnect them as they are reconnected in the graph. But the point is that this is some kind of, it has infinitely many points, right? The points in the interior of edges also count. So the divisor group of gamma is the free abelian group on the set gamma on this metric space. This is an uncountable group. So then you can define chip firing, and in the interest of time, maybe I'll just skip it. So you can define principal divisors sitting inside the divisors 0. And so then you can define the Jacobian, or I mean, I guess this is more accurate to call this pic 0 of a graph as div 0 of gamma modulo the principal divisors. Okay. And so what this is now going to be is this, think of it as the algebraic picture is the picture over C, the graph picture is the picture over Z, this is the picture over R, so this is a compact abelian group over R, so this is just a real torus of dimension G. So in other words, abstractly, it's isomorphic to R to the G mod Z to G. Okay. And in fact, this is something called a tropical principally polarized abelian variety. And then again, in the interest of time, I probably won't define what this is. Okay, but what I want to explain, and again, just to, I'm kind of smashing a lot of theory into one statement. There is an Abel-Jacobi isomorphism between this pic 0 and the Jacobian, and the Jacobian is the one that's properly the principally polarized tropical abelian variety. Okay, so I do want to just very briefly mention one thing, which is I want to compute the volume of this Jacobian, but of course, to compute the volume of a manifold, you need something like a Riemannian metric on it. So how do we get a metric? How do we get a volume form on this Jacobian? So this Jacobian you can think of as something called the one forms on gamma dualized. This is just some vector space isomorphic to RG modulo H1 of gamma Z. And so you can introduce what's called an edge length pairing on H1 of gamma Z. So what is H1 of gamma Z? This is just a set of cycles of the form gamma E over all edges in the graph. So the gamma E's are integers. And it has the property that that the boundary is 0. So if you look at every vertex, the total sum of all edges of gamma E's over the edges coming out of that vertex and the edges coming into that vertex are the same. So the sum gamma E's over all E such that the source vertex of E is V is the sum such that the target vertex of E is V. Oh, so I picked an orientation for the graph, but the definition isn't going to depend on the choice of orientation. And so there is a certain pairing on this vector on this lattice, gamma H1 gamma Z cross H1 gamma Z to R, which works like this. The way I'm going to pair gamma and delta is I'm going to take the sum gamma E delta E times the length of E over all E in the graph. So for each edge, I look at the coefficient in which it occurs in each of the two cycles. I multiply them, and then I multiply that by the length of the edge. Okay. So this gives me an inner product on the corresponding vector spaces, and that's inner product gives me an inner product on the universal cover of the Jacobian, and hence a translation and variant metric on the Jacobian. Okay. So now what I want to do is find a formula for the volume of the Jacobian. And we're going to kind of put our physicist caps on for this. So if G is a finite graph, then the number of elements in the Jacobian, as I said, is the number of spanning trees, which I can write as the sum over all. I don't want a sum over spanning trees. I want a sum over complements of spanning trees. So I want to sum over all F in the edges of G such that G without F is a tree. And what I'm summing is a 1, right? That's how I do my count. So now if gamma is a metric graph, then what is the volume of the Jacobian of gamma? So I want to take this formula and turn it into a formula that has edge lengths in it. And the idea is that the Jacobian of gamma is a G-dimensional Riemannian manifold. So whatever this is, this should be something measured in meters to the power of G, right? So I want to take this formula and turn it into a formula where the units are meters to the G. So how do I do that? Well, there's a pretty obvious way to do this. You see, you sum over you're summing over subsets of the edge set such that the complement is a tree. there means that you're summing over G element subsets of your edge set, right? So the number of elements in F is G. So all you need to do is just take the product of all of the edge lengths in G, right? So you're taking something called W of F, where W of F is just going to be the product over all of F of L of F, right? So this should be the correct formula. But remember at some point oh, there it is. I put a little asterisk here, right? So now let's kind of look at this board and let's see if all the physics makes sense. So you see, at some point I defined an inner product, and that inner product, the inner product of two vectors, is a length. But you see that's wrong. You see the inner product should be measured in units of area, right? How do you find the length of a vector? You take an inner product and then take the square root of it. So somehow these lengths of edges on the graph, they become units of area once you start talking about the Riemannian geometry of the Jacobian, right? Well, yes, that's how it works. So this formula here actually has, it actually has dimension m to the 2g and not m to the g if you think about units of length in the Riemannian geometry of the Jacobian. And so the correct formula, how do you fix that? You just take the square. Yeah, this is how physicists do now, right? Very infuriating. All right, and so this is a theorem of, I should have, well, okay, just erase the statement. This is a theorem of Baker, Kuperberg, Chokria from 2014. Okay, but they in fact, so as kind of a funny little example, if you take gamma to be a circle of length L, of circumference L, then the Jacobian of gamma is also a circle. In fact, gamma is a torsor over its own Jacobian, right? This is kind of like a tropical version of an elliptic curve. But the length of that circle measured in terms of the Riemannian geometry of that circle is actually going to be square root L. This is a circle of length square root L, not L, okay, or volume square root L. Okay, so let me kind of give you a very brief sketch of the proof of ABKS. And in fact, this is a kind of a geometric restatement of an earlier result of Kirchhoff and Jacobian. In their famous 2008 paper, which goes like this. So what you really need to do is you need to look at the G symmetric power of your curve and map it to the pick G of your curve, right? So this is the Abel-Jacobi map. So algebraically, this is a degree 1 map, but of course it's blown up along the theta divisor, right? So what Kirchhoff and Jacobian prove is that this map, in fact, has a canonical continuous section. So given a degree G line bundle, there's just kind of a preferred way of picking a divisor representative for it, whether or not it is special or non-special. And so the way this works is the following. So what is sim G? Well, this kind of has a cellular decomposition considering corresponding to G element multisets of the edge set. So this is a union over all E in sim, I'll call it F in sim G of E of gamma, right, of something called CF. And what is C of F? That's just kind of the set of divisors, each of whose points is supported on a corresponding point of, on a corresponding edge here, right? So if F is a multiset E1 through EG, and CF is the set of divisors of the form P1 of G, such that PI is an EI. Okay. And so we say that this set F is a break set if all EI are distinct and G with F removed is a tree. And so what they showed is that if you think of how phi acts on kind of the individual cells of the G symmetric power, it is injective, right? So this is a dimension G thing. This is a dimension G thing. This is locally just an affine linear map. And so what they prove is that this affine linear map has maximal rank on exactly the break cells. So phi has maximal rank on the break cells. Okay. And furthermore, the image of this section is precisely the set of the break cells. The image of sigma is the set of the break cells. Okay. So locally, the way the Abel-Jacobi map looks like is that, well, the Jacobian, I'm just going to think it locally looks like R to the G, right? So this thing is some kind of polyhedral complex, so it's built up of these parallelotopes. But the way they arrange themselves is that only the ones that correspond to sets of edges which are complements of spanning trees are the ones that are not kind of contracted by this map, right? So these guys are the break cells. And there are many other cells, but they have the property that the map phi always decreases their dimension, right? So the Jacobian is essentially kind of paved by the images of these break cells. Okay. And so then you can compute the volume of the Jacobian by just adding together the volumes of the images of the break cells. So that tells you that the volume of the Jacobian is the sum of the volumes of the break cells. Where does the square come from? Well, so this is a linear map, right? And a linear map has a determinant, which tells you what happens to that volume. And that determinant just so happens to be the reciprocal of the volume that you're trying to compute in the first place. That's kind of this is the way to write down this formula so that it kind of makes sense. How much time do I have?
5 minutes.
5 minutes. Okay, I have 5 minutes to state what our results actually are. So what Yov and I did is essentially all of this for the tropical Prym variety. So So now I want to talk about finally Prym varieties of double covers of Metrographs. So again, I'm going to consider a double cover of a metrograph, which is, there are two ways you can define this thing. The simpler way is what I want to do now, is that just think of this as a topological degree to cover and an isometry. So all of the edges are, each edge mapping to an edge here has the same length. So this is a degree 2 cover and an isometry. So then there are two papers about this. Well, I guess three, including what Yoav and I proved. So this is Jensen and Len in 2018 and Len and Orsh. 20. Which says the following, that, okay, so there is an induced map, F lower star from the Jacobian, gamma tilde to gamma. This map has two connected components. So you can define the Prym variety of the double cover as the connected component of the identity. And this is a tropical principally polarized abelian variety, whatever this is. EPPAB of dimension G minus 1, where G is the genus of the target graph gamma. And just to make sure that Martin is happy, I'm also going to say that, you know, everything tropicalizes nicely. So this tropical principally polarized abelian variety is the skeleton of the Berkovich analytification of the algebraic Jacobian. Okay, and so, well, let me at least state the formula for the volume. Now that our physics intuition is in place, this is a formula you kind of can easily guess what it should be. Volume squared of the Prym variety, gamma tilde over gamma, is the sum over all O-gods of the of gamma. So for each O-god, you take W of F, which is the product of the edge lengths in F. But now each such term you're going to weigh with the coefficient, which is going to be 4 to the power of F minus 1, the rank of F minus 1. Okay. So I have 0 minutes left. Do I have time to do an example in one dimension? Okay, good. It's a one-dimensional example. So there is also, I don't have time to state this, there is a geometric interpretation of this formula in terms of the kind of the tropical Abel-Prym map. So instead of making the statement, let me just kind of draw a picture. So this is my graph gamma tilde. I'm going to look at the following graph. So the edges are going to be of lengths x, y, and z. And so for the pre-image, I'm going to take both of these loops and kind of resolve them like this. And the edges are going to be connected like this. Okay. So these are edges of length x, y, z. And so now I'm going to take my top curve gamma and map it into my Prym variety. And the way this map is going to work is that I'm just going to take each point and map it to the point minus the involution. And so then, so the Prym variety should be a TPPAV of dimension 1. So that should just be a circle. And so what I claim is that this map is actually a harmonic map of degree 2. So this is a 2-to-1 map of metric graphs. And its degree, it's going to be determined by the rank of the O-God represented by each point. So for example, on this, on a point lying above this edge, this is an O-God of rank 1 because removing this edge gives me a genus 1 graph. And so this map has degree 1. So this edge has length x. This edge similarly has length z. But the edge y is an O-God of rank 2 because removing these two gives me 2 connected components. And so in fact, this length is going to be 2y. And so the volume squared of the Prym is just the circumference, right? And so this is going to be x plus 4y plus z. So to answer this question, the 4 appears because 4 is 2 squared, and the 2 appears because those 2's, or those powers of 2, are in fact local degrees of a harmonic morphism of polyhedral spaces